All right, so now let's go from the specific, from the concepts, from the ideas, or from the general rather, to the specific. Let's look at some examples. Maximum and minimum values, finding those critical values. And right now as we look for the critical values, and we want to start thinking to ourselves, what's the nature of these critical values? Are they maximum or minimum values, or is there something else going on at that point? So I've got a couple of examples for us to look at here. So for the first one, I'm going to ask us to make a graph. So bear with me on this. I want to sketch the following graph. It's not a nice, well-behaved graph. So make it kind of nice and big in our notes here. And it's going to look like this. And I'm going to give you some different points. We're going to start right here. I'm going to come down to some point right here. I'm going to go straight across to some point right here, and I'm going to include another point right there. And then I'm going to go up and then down, and then up and then down, and ending right there. And the other values I want to point it out, some point right here, some point here, and here, and here. And I'm going to give each of these points, rather than give them numbers, I'm going to give them corresponding letters. So this point right here is A. This is B. This is C and D. This point up here, we're going to call it E, F, G, and H. And I want to look at all of these points, and I want to ask a bunch of questions about, what's going on here. So as we take a look at this, I want to identify certain things from this graph. First, are there any global max? Global max or absolute maximums here? Well, for one thing, I know that this going from A to H is a closed interval and it is continuous. So my extreme value theorem says that yes, there will be a global max. And where is it? I think we can see that the global max is at point E, my global max. The extreme value theorem tells me that I also have to have a global min. At least one global min. Where is the global min? Well, let's see the small, so it looks like over here it's negative. It looks like it would be at point H. All right, do I have any local max? Any local maximum values? Well, let's see. Local max, I think it seems like I would have one over here at point G. I don't think A is a local max or a local min. It's an endpoint. It certainly isn't a maximum or a minimum. I don't think that's going to help. I think the only local max that I have is point G. How about local min? Why isn't A a local max? Well, the endpoints can be global maxes or mins, but they cannot be local max or mins. So let's see, any local minimum values. I think I've got a bunch of them. I think B and C and D are all local mins. F. What about H? Again, it's an endpoint, so no. It's not going to be, it can be a global max or min, but it cannot be a local max or min. Okay? And I think that's it. I think that's everything that I can tell about that graph. All right, now let's take a look at some functions. Ask the same questions, but this time with a little bit of functions and a little bit of calculus going on. So, find critical values of the following function. F of x equals x times e to the x. And I don't want to graph this. We're not just going to graph this and you know do all the answers graphically. We want to kind of attack this thing with calculus. So I want to do the derivative. So the derivative of the function, clearly I've got a product rule. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. If I clean that up, I get x times e to the x plus e to the x. I can factor out e to the x plus 1. There is my derivative. Now to find the critical values, I'm going to set it equal to 0 and solve. Well, it's already nice and well behaved and factored, so I can say e to the x equals 0, x plus 1 equals 0. If I solve here, if I take the natural log of both sides, I get x equals the natural log of 0, subtract 1, and I get x equals negative 1. And of course, this should jump out at you. This should immediately cause you this cannot be, right? You cannot take the natural log of 0, so there's nothing here. So that's an extraneous solution. It's not even part of the domain. So the only critical value I have in that function is at negative 1. Is that a maximum value? Is that a minimum value? I mean, what's going on there? We could certainly find the slope of the tangent line at the point there if we wanted to, and we could do some other things, but right now I don't care about that. I just care about finding the critical values. Let's look at another example. Let's find the critical values of the function f of x equals x plus the sine of x. And again, the first thing I'm going to want to do here is do the derivative. So the derivative is going to be, now this is just the sum, so the derivative of the sum of the functions is the sum of the derivatives. So the derivative of x is 1 plus the derivative of sine is cosine. And there's my derivative. Now I need to set it equal to 0. 0 equals 1 plus cosine x. Negative 1 equals the cosine of x. And let's see, when is, for what value of x, cosine of what value is negative 1? Again, you should probably be thinking, this should jump into your mind, unit circle, and here's x is negative 1. What is that angle over there? And of course the answer is pi. But it is also a periodic function, so it's going to repeat. What's the period of cosine? 2 pi. So the answer is not only going to be pi, but every 2 pi n after that, where n is some integer. So at pi, and then at 3 pi, 5 pi, 7 pi, 9 pi, or negative pi, negative 3 pi, negative, and so on. So I've got all of those repeating values there. All right, one more example. So I want to find the critical values of the function f of x equals, actually, you know what, instead of doing f of x, let me switch it up on you here a little bit, and you can probably guess what this is and where I'm going with this. But let's do s of t equals t to the fourth minus 4t cubed plus 2t squared. And we can probably guess what this is, what this really is, and what we're really doing here. And of course, the first thing I want to do is I want to find the derivative of the function 4t cubed minus 12t squared plus 4t. And then I want to set the derivative equal to 0. 4t cubed minus 12t squared plus 4t. I noticed that I can factor out a 4 and a t. So 4t, and I'm left with t squared minus 3t plus 1. And clearly 4t equals 0, t equals 0. There is one critical value. How about this one? T squared minus 3t plus 1, set that factor equal to 0. Now, is this going to factor? Think of two things multiply together, give me 1, add up to give me negative 3. No, this is not going to factor very nicely. I can't factor this. How am I going to have to solve this? And if you guessed quadratic formula, you're correct. T is going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. Substituting in, t is going to equal negative 3 plus or minus the square root of negative 3 squared minus 4 times a times c all over 2 times a. T is going to equal 3 plus or minus the square root of 9 minus 4 over 2. Running out of room here a little bit. Let me add a piece of paper here. For my final simplifying, t is going to equal 3 plus or minus root 5 over 2. So what are my critical values? How many critical values am I getting here? I'm getting 3 critical values. What are they? 0, 3 plus root 5 over 2, and 3 minus root 5 over 2. And where do you think that this function came from? What do you think that function really represents? And what do you think is really going on here? What do these values really actually represent? All right, so maximum and minimum should be very familiar, very comfortable, using the derivative, setting the derivative equal to 0 to finding the critical values. Shouldn't give us too much of a difficult time. But as we move on, we're going to start looking at some of the applications of these, and then we're going to take a closer look at the critical values and really determine, the nature of these critical values. All right, should give us enough time to get started on the homework. Good luck.